Good afternoon, dear students. Uh, yes. So, we were discussing about Raoult's law in our previous class, right? So we were discussing about Raoult's law. So we have seen what is Raoult's law, and we had seen the mathematical expression also to calculate the Raoult's law. Okay, so we have discussed the two cases, case one and case two, where case one was about volatile solute and volatile solvent, right? And case two was about both. One was a volatile uh, solvent and another was a non-volatile solute. So these two cases we had discussed based on the Raoult's law. Right. Okay. So today we are going to continue the next part. That is, we are going to see something called as ideal solutions and non-ideal solution. So what do you mean by ideal solutions and what do you mean by non-ideal solutions? Okay. So what are these ideal solutions? So ideal solutions are those which obey Raoult's law at all composition. So they are called as what? They are called as ideal solutions. So ideal solutions, what are these ideal solutions? So ideal solutions are, so this is a important questions, okay, asked in the board exam. So a difference between ideal solutions and non-ideal solution. So what is ideal solution? So ideal solutions are those which obey Raoult's law. Okay. And here that is a composition of the solute in solvent at on all temperatures. So the composition is same of solute in solvent at all the temperature. Okay. Here the interactions. So when you discuss about the interactions, so suppose if I have two different beakers, okay, in one beaker I have a pure substance A. I'll let me pure A, and in another this I have pure B. Okay, so pure B. So here all the molecules are of B. Okay, they are of B. All the molecules, atoms which are present, they are of B, and here the molecules are present of only A. So these are the two pure substances. So when pure substance A and pure substance B is added, we get what? We get a solution. We get solution in which we have both molecules A and B present. Okay. Now, when we are talking about ideal solution, so what is said that the A interaction, okay, so the molecular forces which are present between the two atoms in the pure A, okay, the interaction is same, okay, and the BB interactions in pure B will be equal to AB interactions in the solution. So this is according to Raoult's law. Okay, this is according to Raoult's law. So what is Raoult's law? Raoult's law states that, so whenever the molecules which are present in pure A, so the interaction forces are equal to BB interactions, which is also equals to AB interactions after the solution is formed. Okay, so this is about the interaction. So interactions means what? Interactions means the forces. Okay, interactions means what? Interactions means the forces which are present between the molecules. So the forces which are present between the molecules, they are called as what? They are called as interactions. Okay, intermolecular forces. They are the intermolecular forces. So whenever any ideal solutions is there, okay, whenever there is any ideal solution, so these will follow a set of few criteria is there. Okay, so whenever, so ideal solutions, they obey Raoult's law. Okay, so first thing, it obeys Raoult's law. Second is what? The interactions which are present. Okay, the interactions which are present between AA interactions and BB interactions is equal to the AB interactions in according to Raoult's law. Okay, then the third important point in ideal solution is that uh, delta V mixing is equal to 0. Means what? Okay, delta V mixing is equal to 0 means what? Delta means change. Okay, delta is nothing but change. So the change in volume after mixing the solute and solvent. So what are these? Pure A, you can take this as solute, and pure B is nothing but your solvent. So the so suppose I take here 20 ml of pure solute and I take 20 ml of pure solvent. Okay. Then what is happening after mixing? Okay, after mixing, what you will get? The total volume of solution will be what? It will be 40. So while adding, what is the volume? It is 40, and after adding it is 40. So the delta V, that is volume of mixing after mixing the solute and solvent, is also equal. It is any is there any increase or decrease? No, right? There is no increase nor there is decrease, so it is 0. So always so the third criteria is that delta Vmix is equal to 0. Okay, delta Vmix will be equal to 0. So this is about your Raoult's law. So the third point. Next is what? Next is delta H mix is equals to 0. Okay, means what? The heat absorbed will be equal to heat evolved. So there won't be any additional heat required. Okay, there won't be any additional required. So you can see here, for ideal solutions, delta H mixing will be equal to 0. That is, no heat should be absorbed or evolved during the mixing. So whenever, so for pure solute, so suppose, okay, now when we are means what? So when you are considering about delta H mix, that is change in enthalpy. So this is change in enthalpy. So heat absorbed, okay, heat absorbed will be equal to heat evolved. Heat absorbed will be equal to what? Heat evolved. Okay, means no additional heat is given to the solution. Okay, no, this is now suppose these are two. Okay, your the A interactions are there. So this is a pure component A and this is a pure component B. So your BB interactions will be formed. Okay, so when you add A and B, you will get what? AB type of interaction. So this is about solution. Okay, now solute A. So here for the formation, there will be heat will be required. Okay, heat will be required. Suppose I require 20 joules. Okay, 20 joules of heat is required. For pure B also, what is required? Heat is required. Okay, now here also 20 joules is given. Okay, now here when the interactions are formed, that is AB interactions are formed, what will happen when AB is here? AA interaction. So the bond is required, the heat is required to form the bond between AA, same molecules, right? Same way with respect to B also. So here the heat is required to formation of the bond, right? Now when this AB bonds are forming, what is happening? These interactions, AA bond, what will happen between the AA, yes, whatever the bond is formed, it has to be broken so that the new bond is formed between A and B. So what is happening here? So the heat will be released. Okay, heat will be released. So how much heat will be released? Heat release will be 40 joules, right? Because from AA interactions and BB interactions, when the bond is broken to form the new interaction AB, so the heat release will be 40 joules. So what you can see, that heat absorbed is how much here? 40 joules totally between AA and BB, and heat released will be how much? 40 joules. So here also the change in enthalpy is 0, right? The change in enthalpy is 0. So whenever we are discussing about ideal solutions, so ideal solutions, they obey Raoult's law. Okay, the AA interactions is equal to BB interaction is equal to AB interactions. Okay, and delta H mix. Okay, the change in enthalpy will be equal to 0. So no external heat is required. Okay, during the mixing. Then the next point is delta V mix. Okay, that is a change in volume. Okay, after mixing is also equal to 0. So these are the conditions for the ideal solution. Is it clear? Yes. So what are the examples? So some of the examples of ideal solutions. So you have to remember this. It is asked during exam. Okay, N-hexane and N-heptane. Okay, N-hexane and N-heptane. Then you can benzene. Okay, benzene and toluene. So what are the, yes, now one more thing, what are the criteria? Okay, what is the criteria for the solutions to be ideal? Okay, the first is that between the molecules, okay, they should have nearly same molar mass. Now between this benzene and toluene, the molar mass, okay, or the size should be approximately same. Okay, approximately same. So this is the criteria. Then second criteria is that they should be having same polar nature. Okay, either both the molecules should be polar in nature or they should be non-polar in nature. Okay, so these are the necessary conditions. Okay, these are the necessary conditions. Is it clear till here? Yes. So ideal solutions. What are ideal solutions? Okay, what are the conditions and what are the examples? So examples, we'll see some more examples. So N-hexane and N-heptane, benzene and toluene. Okay, then ethyl chloride and ethyl bromide, and CCl4 and silicon tetrachloride. So these are the examples of ideal solutions. Okay, so next we are going to go for non-ideal solutions. Now, what is this non-ideal solution? So non-ideal solutions are what? Non-ideal solutions are those solutions which do not obey Raoult's law. Okay, so these solutions, they do not obey what? They do not obey Raoult's law at over entire range of composition. So what is happening here? Okay, during the non-ideal solution. So what are the characteristics of non-ideal solutions? So we will see that now. So the first, this is what ideal, non-ideal solutions. These are what they do not follow, they do not obey. Okay, Raoult's law over entire range of composition. Then what are the characteristics? Okay, what are the characteristics? So the first is the enthalpy of okay, the enthalpy of mixing, that is the volume of mixing of the pure component, is not equal to zero. Okay, so we have seen now what do you mean by that? Is when the solute and solvent is added, the whatever the solution is formed, okay, after mixing, the volume is either increased or either it is decreased. Okay, so the change in volume is not equal to zero. Either there will be increase in volume or it will be decrease in volume. So based upon the increase and decrease, the non-ideal solutions are further divided into two types, that is positive deviation and negative deviation. So this also we are going to discuss. Okay, so delta V mixing, okay, delta V mixing is not equal to zero. And one more, the enthalpy change of mixing, that is the enthalpy, that is the heat required and heat released, okay, is not equal to zero. So external heat is required in this, not by the ideal solution. Enthalpy change of mixing of pure components is not equal to zero. So so you have to write as delta H mix, okay, is not equal to zero. So a question is asked during board exam. Differentiate between ideal solutions and non-ideal solutions. Okay, it can be asked for 2 marks or it can be asked for 3 marks. So if it is asked for 2 marks, so you have to write 2 differences. If it is asked for 3 marks, you can write 3 differences, but the difference should be correct. Okay, so what can be the differences? So ideal solutions. So ideal solutions, what will be the first point? Yes, students, what will be the first point for ideal solutions? You can unmute yourself and you can answer. No problem. So what is the difference? First difference between ideal and non-ideal?
Ideal solutions obey Raoult's law.
And
It does
non-ideal?
not obey Raoult's law.
Yes. Okay, so this
And
is our first point. Second point?
no heat should be observed or evolved during mixing in ideal solution.
No, what you can write is delta H mix is equal to 0 here. And here you can write delta H mix is not equal to 0. Okay, so that is the enthalpy change of mixing of pure component is not equal to 0, and your delta, the enthalpy change of mixing of pure component is not equal to 0. So this can be the second point. Similarly, third point is what? Here the volume of mixing, okay, the change in volume of mixing is equal to 0. So that is delta V mix is equal to 0, and here delta V mix is not equal to 0. Okay, so the volume change of mixing of pure component is not equal to 0 in this non-ideal solution. Then the fourth point can be interaction. A interaction is equal to B interactions is equal to AB interactions. In this, it is A interactions is AA interactions, BB interactions is not equal to AB interaction. Okay. So these are the major differences. So depending upon this, so now the ideal solutions, as we have discussed, it is further divided into two types, that is positive deviations and negative deviations. So non-ideal solutions which is showing positive deviation means what? The values are a bit higher. Okay, when it has the value bit higher, then it will show positive deviation. When it will have the values means the after mixing or after this, if the volume is a bit less, okay, so then it is negative deviation. So the what are the examples of negative deviation? Sorry, non-ideal solutions. Okay, what are the so in this again we'll study with respect to this only, positive deviation and negative deviation only. We'll study the examples. Okay, so here what will happen when you have a positive deviation? So this is an example of positive deviation. You can see this, the graph. You can see how the values are greater, right? So here you can see the value vapor pressure of the solution is greater than the okay, your so this is your Raoult's law. So this is according to Raoult's law, the green line indicates this is what the values are bit greater. Okay, so the vapor pressure is bit greater, so this is indicating your positive deviation. So PA is greater than your psi A, and PB is greater than your psi B. Okay, then what will happen after mixing? That is the delta H mix, okay, will be greater than 0. So mixing of pure component is your endothermic process. What it is? It is a endothermic process. Okay, about positive deviation. Then delta V mix. Okay, the change in mixing of volume is greater than 0. Okay, it is greater than 0. Then what about the interactions? The in such solution, okay, in such positive deviation solution, the intermolecular interactions between the molecules, okay, are weaker. Here they are weaker than those between the molecules of pure components. So A interactions and BB interactions are a bit weaker. Okay, that is your AB interactions. It is bit weaker than your AA and BB interactions. So this is the criteria. So the molecules, what they'll do, the tendency of the molecules from the solution into the vapor phase. So whatever the molecules are there, they have the tendency to go into the vapor phase. It increases, okay, and thus it results into what? It results into a positive deviation. So the molecules present in the solution, they have the tendency to convert into vapors, and thus they form a positive deviation. So what are the examples? The examples of positive deviations are N-hexane plus ethanol. Okay, N-hexane plus ethanol. Then ethanol plus water. Okay, please write it down. Very important. So it is asked during example. So it can be asked during CET like that. Okay, N-hexane plus ethanol is an example of what type of deviation. Okay, ideal solutions, positive deviation, negative deviation, or none of the above. Like this, anything can be asked. So like this, so you have to remember the examples. So acetone plus carbon dioxide, carbon disulfide. So these are the examples of what? These are the examples of positive deviation. Okay, chloroform CHCl3 plus CCl4. Then acetone plus benzene. Okay, so these are some of the examples of what? These are the examples of positive deviation. Is it clear? Positive deviation. Okay. So we are going for negative deviation. So this is a negative deviation. So in negative deviation, what is formed? Yes. So the non-ideal solutions, which is showing the negative deviation from Raoult's law. So ideally, this is the green dots. Okay, green dots represents your Raoult's law. So we have plotted Raoult's law, the graph of Raoult's law in the previous session. So now you know that. So this is what happens during non-ideal solutions. So the solutions, that is non-ideal solution which does not obey Raoult's law. So it is deviating. Okay, it is deviating. It is showing negative impact. So what is happening here? That is PA. That is PA is greater than psi of A, and PB is greater than. It should be less than. Okay, it should be less than. So make this correction. It should be less than. So the partial pressure is less than the psi of B. Okay, so you can see the vapor pressure has decreased. Okay, blue, it shows the deviation. It has a negative impact. Lower, the slope is lower, right? So make this correction. Then, so what is the first point for such solution? Okay, delta H mix, what will happen to delta H mix is less than 0. So what happens after mixing the pure component A and B? Okay, the solution, resulted solution will be exothermic in nature. Okay, it will be exothermic in nature. So what will happen to delta H value? Delta H value, that is after mixing, will be less than 0. Okay, then delta V mix. Okay, delta V mix is also less than 0. That is after the mixing of the component A and B, the solution which is resulted, okay, the solution which is resulted, the volume is less than 0. Okay, it will be less than 0. So delta V mix will be less than 0. So the volume of the solution is less than that of the volume of individual component. Means what? Suppose I have pure component A and I have pure component B. And after we add this, we get the solution AB. Okay, so this is a solution. So you can consider this as solute. You can consider this as solvent. Suppose I have taken this as 20 ml. This I have taken as 10 ml. Okay, I have taken as 10 ml. So the resulted solution is 25 ml. Okay, so this is what? This is 30 and this is 25. So the whatever after mixing, the solution which we have got is less than the individual component. Okay, so this it means. So after mixing in non-ideal solution, what happens? The volume is less than 0. Okay. Then in the interactions, okay, what happens to interactions? So the intermolecular interaction between the molecules of these pure components, okay, that is AA interactions and the BB interactions. Okay, what will happen? In such solutions, the intermolecular interactions, okay, what will happen? The molecules of this pure component AA and BB, okay, the tendency of the molecule to, what will happen? So in the positive deviation, what we have seen, the solutions, what the molecules in the solution, they try to escape as vapors, okay, but here the tendency of the molecules to escape as vapor phase will decrease. The tendency of the molecules from the solution to escape as vapors will decrease in your negative deviation. Okay, so this is the interaction. So due to this interaction, so your because of this, it results into a negative deviation. Understood? So this is about negative deviation. As in case of positive deviation, we have seen what happens. The molecules which are present in the solution, they will escape into, it will escape out in the forms of vapors, okay, and the vapor formation will be more, it increases and it results into a positive deviation. But here, what will happen? The tendency of the molecules to escape out in the form of vapors will decrease. So it will result into a negative deviation. So this indicates a negative deviation. Okay. Now, what are the examples of negative deviation? So please note it down. So phenol plus aniline. Okay. Then chloroform CHCl3 plus acetone. Okay, acetone. Then chloroform plus diethyl ether, then acetone plus aniline, then chloroform plus HNO3, water plus HNO3. Okay, so these are some of the examples of what? Negative deviation. So this is a graph of negative deviation. Is it clear? What is ideal solutions? What are non-ideal solutions? What is a positive deviation? What is a negative deviation? Is it clear up to here? Yes? Okay. Okay. So we'll proceed further. So next is azeotropes. Next is what? Azeotropes. Now, what do you mean by this azeotropes? So azeotropes, it is a liquid mixture, okay, and it boils at a constant boiling point. So it has a constant boiling point. So it is a liquid. So you can note it down. What are azeotropes? Azeotropes are a liquid mixture, okay, and these liquid mixture, they boil at a constant temperature, okay. So such a liquids, they are called as what? They are called as azeotropes. So what are azeotropes? So azeotropes, they are called as a liquid mixtures which have constant boiling, okay, or they are called as constant boiling liquid mixtures. Okay, so the mixture, liquid mixture which boils at a constant boiling point. Okay, so they are called as azeotropes. Fine. So azeotropes are what? Azeotropes are the mixture of liquids which are having same composition in liquid as well as in the vapor phase, because as it is boiling, as we are discussing, what? It is a liquid which is boiling, okay, at the same boiling temperature. Now suppose water is there, okay, suppose water is there. If we boil, okay, if we boil it continuously, sorry, if we heat it continuously at some temperature, what will happen? Okay, if the heat is supplied continuously, okay, so water will start evaporating. Okay, the water will start evaporating. It will be converted into vapor phase. So at some, after 2 hours or maybe after a hour, what will happen? You can see the volume of water has decreased. Okay, it is starting to escape out as a steam or vapors, right? So you are in azeotrope. So this liquid mixture, okay, they are boiling at a constant temperature, at a constant boiling temperature. Why? Because they are having same composition. They are having same composition in liquid as well as in vapor phase. Okay, in the vapor phase and also in the liquid phase, the composition is same. And because of this, it boils at constant temperature. So it boils at what? At constant temperature. Okay, boils at constant temperature. Okay, so it is not possible. We cannot separate the components of this azeotropic mixture. Okay, we cannot separate whatever the composition is present in the azeotropic mixture. We cannot separate these components. Okay, we cannot separate it by distillation also. Okay, distillation is a process in which we can separate a mixture of two different liquids. Okay, we can separate two different liquids at different so it depends on the, so it is it the principle depends on the difference in boiling point of the liquids, any two liquids. Okay, so any two liquids, so the boiling point will be different. So based upon the difference in boiling point, the whenever you have any two liquids mixed, so we can separate it with distillation. But this azeotropic mixture, it cannot be separated by distillation also. So here, so you can see, okay, so the liquid, so this is a liquid composition. So vapor only. So the azeotropic mixture, which is boiling at constant temperature. Okay, it has the same composition in liquid phase as well as in the vapor phase. Okay, and these such a liquids are called as what? Azeotropic mixtures. So these azeotropic mixtures, they are further divided into two types. Okay, what are the two types? First is minimum boiling azeotrope. The first one is minimum boiling azeotrope, and the second one is maximum boiling azeotrope. Now we are going to discuss what do you mean by minimum boiling azeotrope and what is mean by maximum boiling azeotrope. Now, what do you mean by minimum boiling azeotrope? So the solutions, okay, you can see this is a graph of minimum boiling azeotrope. So the solutions which shows large positive deviation from Rawls law. So you can see the deviation is large. Okay, you can see the positive deviation, right? So what is happening here? These minimum boiling solution, they show positive deviation from Raoult's law, and thus they form minimum boiling azeotrope at a specific temperature. So at this temperature, you can see at a specific temperature, okay, what is happening? So this is a temperature. So this is a temperature. Okay, so at a specific temperature, what is happening? The this azeotropic mixtures are formed. So this is a minimum boiling azeotrope. So how minimum boiling azeotropes are formed? They are formed by solution with positive deviation, okay, from Raoult's law. So what are the examples? Examples are very important. Ethanol plus water, okay, ethanol plus water, ethanol plus water containing, so this should be mentioned, okay, containing 95% by volume of ethanol. So this is an example of azeotropic mixture. Ethanol plus water containing 95% by volume of ethanol. So this is what? Minimum boiling azeotrope. Okay. Now what are maximum boiling azeotrope? Yes. What do you mean by maximum boiling azeotrope? What will be maximum boiling trope? Yes. So the solutions which shows large negative deviation, okay, from Raoult's law, they are called as maximum boiling azeotropes at a particular composition. Now, what is the example for maximum boiling azeotrope? There are two examples, so you can note it down. Water plus HCl, water plus HCl, that is hydrochloric acid, containing 20.2% HCl by mass. Okay, and one more example, water plus HNO3. Okay, water plus nitric acid, water plus nitric acid containing 68% nitric acid by mass. Okay, so these are the two examples. Understood what are azeotropes and what are the types of azeotropes?
Yes, ma'am.
Okay. Others? Okay, so azeotropes. So remember what are azeotropes? So these are the liquid mixtures which boils at constant temperature. So they have a constant boiling temperature. Okay, so there are two types: minimum boiling azeotrope, maximum boiling azeotrope. So minimum boiling azeotropes, they will form positive deviation from Raoult's law, and maximum boiling azeotrope, they form negative deviation from Raoult's law. Okay, so examples are very important. So water ethanol system and is example, best example of minimum boiling azeotrope, and water, this water HCl and water nitric acid. Okay, the composition is very important. I had written here, right? See here, I had written here 20.2% HCl by mass, 68 by 60% HNO3 by mass. So this composition is very important, okay, during exam. So if you do not write this complete example, the marks will be deducted. So you have to write the complete ethanol plus water containing 95% by volume of ethanol. Okay, like this, the complete this composition should be written, because what is important in azeotropes? The composition is important, right? Because the composition is same at a liquid state as well as in the vapor state. So because of that, the composition should be written correctly. Okay, so these are the two types of what azeotropes. So next we are going to discuss about the colligative properties. Okay, so the next important thing, okay, in the solutions chapter are the colligative properties. Now, what do you mean by colligative properties? Okay, so uh, whenever you have some non-volatile, the dilute solutions, okay, whenever you have some dilute solutions of non-volatile solute. Now you know what is volatile, what is non-volatile. Non-volatile means what? Non-volatile means they do not produce the vapor state, right? They do not produce vapors. So the solute, okay, whenever you have the dilute solutions of non-volatile solute, okay, solute are those which will be present in the smaller quantities. So these solutes, they will show what? They will show some specific characteristics. Okay, they will show some specific or certain characteristic properties. Okay. Now the properties of these solutions. Okay, the properties of these solutions, they depend only upon the number of solute particles. So whenever we are discussing about the solution topic, what happens? It depends on what? It depends upon the number of solute particles. It depends on the number of solute particles. Okay, that is how many numbers of molecules or the ions are present. How many number of molecules or the ions are present, and it does not depend upon the nature of solute. It does not depend on nature of produce. So colligative properties. So whenever we are discussing about colligative properties, it depends on what? It depends upon the number of solute particles. It depends on the number of solute particles and not on the nature of solute particles. So these are called as colligative properties. So there are four important colligative properties. Okay. So the four important colligative properties of solutions are, first is the lowering of vapor pressure, that is relative lowering of vapor pressure. Then is elevation in boiling point. Next is depression in freezing point and osmotic pressure. So based on this, you will be get. So the this is a physical chemistry chapter. As you all know, solution chapter, it comes under physical chemistry. Okay. So in physical, when you might have seen now in your first year also, right? Physical chemistry, the questions are asked in separately in one part, right? Part D or part E. So there separately the questions are asked from that particular chapter. So from this chapter, you are going to get the questions from this, so this part, okay, colligative properties. So there are different formulas, okay. Based on that, we are going to solve the problems. So first we'll see what is lowering or these four properties. So colligative properties, they depend on what? They depend upon the number of solute particles, and they does not depend on nature of solute particles. Okay. So the four important properties: relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay. So we'll start with one. So first we'll see the relative lowering of vapor pressure. First is what? Relative lowering of vapor pressure. So whenever you have a non-volatile, so this condition we have seen, where we have seen this condition, relative lowering of vapor pressure, when we are discussing the Raoult's law. In Raoult's law case 2, yes, in Raoult's law case 2, we have discussed about relative lowering of vapor pressure. So I'll not go much into detail. Okay. So I'll just, so this is based on the Raoult's law. So relative lowering of vapor pressure. So whenever you have a non-volatile solute, right? Whenever you have a non-volatile solute and you have a volatile solvent. So this was a case 2, right? So whenever you have a non-volatile solute and you add this non-volatile solute to a volatile solvent, what will happen? The vapor pressure will get lowered. That you know now, right? Or I should tell you. See here, I had discussed this. So only once I'll tell you. So when if you have a solute, okay, now this is a solute. So these are the, I'll take this as solvent now. And this is a non-volatile solute. Non-volatile solute means what? They will not produce any. So these will produce the vapors because solvent is a what? Solvent is volatile. So volatile solvent will produce the vapors. Okay. And non-volatile solute will what? It will not produce any vapors. Okay. And when you mix this two, that is solvent and non-volatile solute, you get a solution. Okay. And what will happen? So these are also non-volatile. So what will happen? What will happen when you form the solution? You can see that the molecules of volatile and non-volatile will be present at the surface. Okay, and the molecules of volatile solvent only forms the some of the this papers, right? So what is happening as compared to the pure solvent? Okay, and in the solution, the formation of vapors will be less in the solution. So vapor pressure, what will happen to vapor pressure? As the number of vapors are less, okay, the dynamic equilibrium reached will be, okay, it will be lowered in the dynamic equilibrium. Thus, the evaporation process will go at a slower rate. Okay, so number of vapors produced will be less and the vapor pressure exerted will be less. So this is about relative lowering of vapor pressure. Now we'll apply the Raoult's law. So vapor pressure of the solvent in the solution is equal to the mole fraction of the solvent in the solution into vapor pressure of the pure solvent. That is vapor pressure of component A is equal to mole fraction, that is pure vapor pressure of pure component A into mole fraction of pure of a component A, right? So here we okay, so what is PA? So we know that mole fraction of A and B component will be equal to 1. Okay. Now what we have to put here? So I take this PA is equals to P naught of A. Okay. Now what is psi A? So psi A can be 1 minus psi B. So I'll write it as 1 minus psi B. Okay. Now you take PA is equals to P naught A. P naught A into 1 will be minus P naught A into psi B. So what happens here? The solute is non-volatile, right? The solute is non-volatile. Then the vapor pressure of the solvent will be equal to vapor pressure of the solution, right? So what will happen here? So P is equals to, so we are taking, so vapor pressure will be equal to the vapor pressure of the solution. So P, the total pressure will be equal to P naught A into P naught A into psi of B. Okay, so vapor pressure minus P is equals to, so I'm taking this common. So when you take it this side and it will be P naught of A into psi of B. So I am transferring of minus B into P naught A is equals to B. So this is the, when your solute is non-volatile. Okay, when the solute is non-volatile. So this is the equation which you get. Okay, so this is the, now you know how to find the mole fraction, right? Mole fraction can be found out what? Number of moles of component A upon total number of components A plus B. So by applying that, you will get the formula, this one. Okay, so that is how you count number of moles. Number of moles is given weight. Okay, given weight upon molecular weight. Given weight upon molecular weight is number of moles. Okay, so number of moles, so given weight can be written as W and molecular weight is written as M. So we are having psi A and psi B. So how we'll write? So W A, okay, W B. Okay, because solute will be in the topper. Okay, so P naught, this is pure component A minus P is what? It is nothing but the lowering of vapor pressure. Okay, and this this related to P naught A, and this is called as relative lowering of vapor pressure. And you know how to calculate the psi of B. Psi of B can be calculated as number of particles of that is, this represent the number of moles of component B upon total number of moles of A and B. What is Na? That is, just now I told you, number of moles can be calculated by given weight upon molecular weight. Same way with respect to Na, that is Nb, that is number of moles of B, given weight of P upon given weight of molecular weight of the solute. Okay, so by putting this into this equation, you will get the final equation. So remember this final equation. This final equation is very important. Okay, by using this equation, we are going to use the formula. Okay, we know what is psi of B. After getting this, okay, after getting this, what we have done, psi B is nothing but number of moles of B upon Na plus Nb. So after that, we have put this values. Okay, Nb is what? Nb is Wb upon Mb. Okay, Na is what? Na is this what? Wa upon Mb. So after putting this value, you will get the final equation. Is it clear? Relative lowering. So this we have solved during the case 2. Okay, so by using this formula, we are going to use the, yeah, we are going to find out the relative lowering of vapor pressure. So relative lowering of vapor pressure is equal to mole fraction of the solute in the solution. Is it clear up to here? Yes, relative lowering of vapor pressure. So when we'll be solving the problems, you will come to know. So these formulas are very important. Okay, you have to remember this formula so that when we are solving the formulas, you will come to know the exact what we are going to do. So you know how to find the mole fraction, how to find the number of moles. Okay, this is number of moles of component A, and this is number of moles of component B. Okay, component A is your solvent, component B is your solute. Okay, so by using this, we are going to use this final equation of relative lowering of vapor pressure. Okay, going for next. Next is elevation in boiling point. Next is what? Elevation in boiling point. Okay. So you can see that boiling point of a liquid. What do you mean by boiling point of a liquid? So whenever you have a boiling point of a liquid, the temperature at which its vapor pressure becomes equal to the atmospheric pressure. So whenever you are calculating the boiling point of a given liquid, what will happen? The temperature of temperature of its vapor pressure, okay, will be equal to the atmospheric pressure. So boiling point is nothing but it is a temperature. It is that temperature where its vapor pressure will be equal to its atmospheric pressure. So as the vapor pressure of the solution containing a non-volatile solute is lower. Now you know how the this is lowered. Okay, how the vapor pressure of the solution is lowered when you add a non-volatile solute, because non-volatile solute cannot produce any vapors. Okay, so when you add the non-volatile solute into the solution, then vapors are not formed, right? Then the pure solvent. What will happen? The boiling point will be higher than that of a pure solvent. So when you add the so the when you add a non-volatile solute, okay, when you add a non-volatile solute into the volatile solvent, okay, into the volatile solvent, so what will happen? There will be increase in the boiling point. So the boiling point of this solution will be higher. So this increase in boiling point is nothing but it is called as elevation in boiling point. It is called as what? Elevation in boiling point. So it is represented as delta TB. It is represented as what? Delta TB. Okay. Now delta TB, it can be calculated as delta TB is equals to TB minus delta TB is equals to TB minus T naught B. Okay. So this delta TB will be equal to KB into M. And what is M? M is your molality. Okay. And KB is what? KB is the molar elevation constant. It is a constant. Okay. It is a constant. It is called as molar elevation constant. KB. Kb is nothing but your molar elevation constant. And the molecular mass, okay, and the molecular mass of the solute. How it can be calculated? I'll give you the formula. Just a second. So the molecular formula, okay, it can be calculated by WB is equals to 1000 into Kb into WB divided by delta TB into WA. So this is a formula by which we can calculate the elevation in boiling point. Okay, this is the, so you can see the graph is given. Okay, whenever you have a pure solvent, its boiling point is at this temperature. Okay, but when you have a pure solvent and with that, when you add a non-volatile solute, what will happen? The boiling point will be a bit higher. So the solution containing a non-volatile solute and a pure solvent, okay, volatile solvent, the boiling point is bit higher. And this increase in boiling point is nothing but called as what? Elevation in boiling point. And this is a formula. Okay, this is a formula by which we can calculate the elevation in boiling point. So this is a formula which we are going to make use of. Is it clear? Yes. So this is the formula from molality. Okay, from molality we are going to get this particular formula. So what are the values? Kb is nothing but Kb is the molar elevation constant. Okay. And your this what? Delta TB. Delta TB, it represents your elevation in boiling point. Okay. And this is the formula. So please note this formula. So based on this also, we are going to solve some problems. Okay. Then so two more we are left with freezing point depression and some more are there. So this we shall discuss it in the next class. Okay. Any doubts in the today's session, students? Any doubts? Do you have any doubts up to here? So we have discussed today what are ideal solutions, what are non-ideal solutions, types of non-ideal solutions. Then we had started with then we discussed about azeotropes, types of azeotropes. Okay. Minimum boiling azeotropes, maximum boiling azeotropes. Then we had started with colligative properties. So we have discussed today two colligative properties. First one is the this one. Relative lowering of vapor pressure, and second one was elevation at boiling point. So we are left with two more, freezing point, that is freezing point depression and osmotic pressure. Okay, and some more points are there, so that we shall be discussing in the next class. Any doubt up to here? Yes, any doubts in today's session?
No, ma'am.
Okay, others? So this part, okay, colligative properties, these four important colligative properties. So this from this this will be asked. Okay, problems will be asked. So these problems are very important. So this after completing the chapter, we will see the problems. Okay, fine. So if there are no doubts, so I shall end the session here. Okay, so we will be meeting in the next class on Monday. Okay, so thank you, dear students. I hope you have understood whatever has been told. Okay.
Yes, ma'am.
Yes. Okay. Thank
Thank you so
you.
much.
Yes. Thank you.
Yeah.